We've looked at mappings between objects within a category, but of course it is also possible to map between categories using a new type of transformation which we will call a functor. So a functor going from a category C to a category D called F will map both the objects of C into the objects of D. Here we see that C gets mapped to FC, and morphisms of C to morphisms of D. However, we need to do that according to certain rules. One is that we need to choose whether we are using a covariant functor or a contravariant functor. A covariant functor will follow the following rules. A morphism F from A to B will get mapped to a morphism F of F from F of A to F of B. Of course, the morphism F is in category C, and the morphism F of F is in category D. If we are using a contravariant functor, on the other hand, we will flip the order that the arrow goes in. So in this case, a morphism from A to B will get mapped to a morphism F of F from F of B to F of A. Notice here how the domain and codomain of the morphism in the category D have flipped. The identity morphism will always map under any functor back to the identity morphism on the object that F maps A to. And finally, composition will be preserved, whether we do that in a covariant way according to this formula or a contravariant way according to this formula. Arguably the simplest type of functor is used to forget certain mathematical structure while mapping objects to themselves in a different category. And these are called forgetful functors. So we know that there's a category of all groups, and we know that there's a category of all monoids, and we know that every group is a monoid, since groups satisfy the same axioms as monoids and some other conditions as well. So we, of course, could just map every group in the category of groups to itself in the category of monoids, since we know that we'll always find every group in the category of monoids. And every group homomorphism is also a monoid homomorphism, and so we can also map the group homomorphisms to the monoid homomorphisms in the category of all monoids. Also notice, of course, that since morphisms are just mapping to themselves, the identity morphism will map to the identity morphism, and the composition of morphisms, say A composed with B, will map also to A composed with B in the category of monoids. And so we see this really is a forgetful functor. It is simply including this pattern from the category of groups, and in fact every pattern in the category of groups, in the category of monoids, and just forgetting that they are groups as well. There's certain additional structure that these patterns are following, but that is not accounted for in the category of monoids. We've forgotten the fact that these are groups. Now, of course, every monoid is also a set as well. So we could repeat this exact same pattern going from the category of monoids to the category of sets. We simply map every monoid to itself as a set in the category of sets. and every morphism from itself as a monoid homomorphism to a set function. Of course, again, identities will map to identities and compositions will map to compositions. And so we have a forgetful functor from the category of groups to the category of monoids, as well as a forgetful functor from the category of monoids to the category of sets. And of course, we also have a forgetful functor going from the category of groups all the way to the category of sets. We, of course, don't need to stop through the category of monoids. We can simply include every morphism and every object in the category of groups as themselves in the category of sets. The next example of a category we'll look at is when we literally want to sort of sketch out a certain pattern that exists within our category. So maybe we have a category C which has various objects and morphisms going between them, but we're only interested in this pattern here, this morphism going from here to here and this morphism going from here to here. This is some interesting pattern within a larger category that we're interested in. Well, to be able to restrict ourselves to just that portion of the category, what we can do is that we can create what we might call a dummy category or an index category, which has only that pattern within it. So we take just these two morphisms, reconstruct the pattern that we're interested in, perhaps call this category J, our index category J, and then we use a diagram functor, or just a diagram, which is a functor D going from our index category J to our target category C. This is helpful because it helps us to accomplish our goal of zooming in on this particular pattern in the category. All we need to do now is to simply restrict ourselves to the image of our functor, and we will have only the part of the category that we're interested in that we have constructed in our index category. Now, of course, the diagram is a true functor by definition, and therefore we need to be careful that our index category is in fact a category so that this can be a properly defined functor. And of course, if these were the only morphisms in our index category, this would not be a full-fledged category because we don't have identity morphisms, and we also need to be able to compose these two morphisms, and we don't have a morphism going from this object to this object. However, what we say is simply that in an index category, we can always refer implicitly to the identity on any object in our index category or to the composition of any two morphisms in our index category. And now this definition will work. This allows us to sort of draw a diagram of a pattern within our category. The final example of a functor that we'll look at here is an important one which comes up often in category theory, called the home functor. So if we fix an object A in a category C, we can define both the covariant and the contravariant home functor. The covariant home functor is denoted home A blank, whereas the contravariant home functor is denoted home blank A, both going from the category C to the category of sets, according to the following definition. So home A blank applied to an object X in C will get mapped to the home set going from our fixed object A to the object that we're applying it to, x, whereas the contravariant home functor will go the opposite way. So home blank A applied to x will give us the home set from x to A. So in some sense, you can see we're simply filling in the blank with whatever the object is in either case. And we can see that we are sending objects of C to sets in the category of sets, specifically home sets. Now, of course, functors map both objects and morphisms, so we need to see what happens to the morphisms of C when we apply the home functors. So in the covariant case, if we have a morphism f from x to y, then when we apply the home functor, home a blank, we know that we need to get back some sort of function which goes from the home set ax to the home set ay, since that is what these objects will get mapped to by the home functor. And indeed, to do this, we're just going to define a new function called follow by f, which is fairly self-explanatory. If we take any morphism in the home set ax, call it t, and we apply follow by f to that morphism, then we simply compose on the left with f to get indeed a morphism from a to y. Similarly, in the contravariant case, when we apply home blank a to a morphism f from x to y, we need some sort of function that goes from the home set ya to the home set xa. And to do this, we're going to define, in this case, the precede by function, which simply takes whatever morphism we're applying it to and composes on the right this time. So if we take a morphism t from y to a, then we simply compose with f on the right, which will indeed give us a morphism from x to a. To see these functors a bit more visually, first, suppose we have our morphism f from x to y, as well as our fixed object a. Well, then we know that the object x will get mapped by the home functor to this home set here, all of the morphisms going from a to x, and our object y will get mapped to this home set here, all of the objects going from a to y. And if we have any morphism in this home set, call it t, then we simply compose with f to get f after t, which will exist in this home set over here. On the other hand, in the contravariant case, the arrows go the other way, so this object x will get mapped to this home set going from x to a, and this object y will get mapped to this home set going from y to a. And since this is contravariant, we start with a morphism over here this time, call it t, and to get our image under the functor of that morphism t, we simply compose with f on the right this time, so we apply f first and then t to get t after f, which is going to be a morphism in this home set. Let's now show that these home functors do in fact satisfy the definition of a functor. So first we need to show that they map identities to identities. So if we apply home a blank to the identity morphism on x, we get 1x and follow by, but follow by 1x applied to some t from a to x will be 1x composed with t, which of course is just t. But that means that this is an identity function on the home set from a to x. That is, followed by 1x is the same as the identity morphism on the home set from A to X. In the contravariant case, this is going to be precede by 1x when this is applied to some t, in this case from x to a, we get t composed with 1x, which again is just t. So we see that in this case we have the same thing, except with the home set going in the other direction. Next, we'll need to show that these home functors satisfy preservation of composition. So in the covariant case, if we apply home A blank to the composition of G and F, where F goes from X to Y and G goes from Y to Z, then we get G after F with a follow by the definition of the covariant home functor. So if we apply that to some t going from A to X, what we get is G composed with F composed with T, but that's equal to G after followed by F applied to T, which itself is equal to followed by G applied to that result, followed by F applied to T. But these are both functions, so this is just function composition. But this is the covariant home functor applied to G, and this is the covariant home functor applied to F, all of that applied to T, which shows that this does satisfy preservation of composition. Similarly, we need to show that the contravariant home functor also preserves composition. So in this case, we're applying home blank A to the composition of G and F, which will give us precede by G after F. So if we apply precede by G after F to some t going from X to A, then we get T after G after F. But this is precede by G applied to T after F, which itself is precede by F applied to that result, precede by G applied to T. And since these precede bys are just function definitions, we can compose them. But that just gives us the contravariant home functor applied to F after the contravariant home functor applied to G applied to T. So both the covariant and contravariant home functors both preserve identities and preserve morphism compositions. We'll conclude by reviewing a few specific types of functors. So if F is a functor from a category C to a category D, then F is called full if all of the home set mappings of F are surjective. So suppose two objects in D which get mapped to by F, say F of A and F of B, then all of the morphisms between those two will get mapped to by F. So we will have two objects in C, either A as the domain and B as the codomain, if this is a covariant functor, or B as the domain and A as the codomain, if this is a contravariant functor, and that mapping must be surjective in all cases. Next, F is called faithful if all of the home set mappings this time are injective. So in this case, rather than a surjective mapping, we need to have an injective mapping. And finally, F is an embedding if it is full, faithful, and the object mapping is injective. So we have that all of the home set mappings are surjective and all of the home set mappings are injective, meaning of course that all of the home set mappings are bijective, and the objects of C map injectively into the objects of D by the functor F.